These liquid metal droplets seem to have developed a life of their own. They move all by themselves without electrical or magnetic fields. The droplet movement resembles that of amoebas. Just to show you how striking this resemblance is, let's put amoebas and the droplets side by side. This is the first step in the development of amoeba robots. The metal droplets are just a few millimeters in size and move on a graphite plate immersed in an alkaline electrolyte. This chemical reaction is one of the very few, if not the only one, that is able to...
What you're about to see is the first ever living robot that was just created by researchers in the US. This is it, the Xenobot. Under 1 millimeter in size, it's unlike most robots in that it's not made of any plastic or metal, but entirely of organic cellular material. It can move forward, turn around, sometimes spin in circles, and if you flip it on its back, it will flip itself back over. It's a human-made robot, but it's alive.
The surface tension variations causing locomotion resemble indeed the process found in living Lobos amoeba, where the function of the ectoplasm and the ectoplasmatic contraction tube is based on similar surface tension effects.
Cyborg beetle project, a man named Hirotaka Sato from Nanyang Technical University in Singapore and his colleagues have combined electronics with live beetles to allow the beetles to be remote controlled by humans. By implanting 6 electrodes into the beetle's wing muscles and powering them with a lithium battery, scientists have harnessed control of this beetle's flight. Not only can they control which direction the beetle flies in, but they can also make it land, take off, or hover in place. Should this technology be developed further, its uses are boundless. It could be used for exploration, espionage, or even communication by the attachment of small microphones. Beetles are the perfect insect for the project. Because they are relatively strong, it's easier to attach electronics and sensors without weighing them down. Number 6. Robo-Bee. After 12 years of research, Harvard scientists were able to create a tiny flying robot known as Robo-Bee. Robo-Bee isn't any normal micro-robot or insect-like drone. Robo-Bee was one of the first robots to achieve flight. With a wingspan of only 3 centimeters, Robo-Bee is the smallest insect-like robot that can fly. That's not all. Robo-Bee solved 2 previously unconquerable challenges that come with micro-robots. First, Robo-Bee was built through a process that was inspired by pop-up books that allows engineers to build on such a tiny scale. Second, to be able to fly, Robo-Bee contains man-made muscles that beat its wings 120 times per second. The aim of Robo-Bee is to eventually develop a fully autonomous swarm of flying insect robots. Theories for its applications vary greatly, from search and rescue missions to crop pollination. The greatest challenges with the development of Robo-Bee, however, are supplying power and decision-making capabilities. Currently, Robo-Bee is connected to a small tether that supplies its power and allows someone to control it. To reach its goals, the development of Robo-Bee has been divided into 3 categories: brain, body, and colony. Development of the brain consists of dealing with Robo-Bee's sensors, electronics, and ability to mimic insect behavior without a human controlling it. Body development consists of Robo-Bee's physical construction and engineering, including its ability to fly. Finally, colony development emphasizes Robo-Bee's ability to function in a full swarm of Robo-Bees, with each one behaving for the benefit of the swarm. Number 5. RoboFly. The idea of robots the size of insects brings optimism to many people from many industries. Whether it's spying on enemy soldiers or inspecting crops on a farm, the possibilities are endless. But insect-like robots are not easy to engineer. Because insect robots have such tiny wings, it's very limiting on how heavy the electronics can be. Hence, why Robo-Bee needed a small tether. Fortunately, a group of engineers from the University of Washington, including one who also worked on Robo-Bee, has also developed an untethered flying robotic insect. Known as RoboFly, this machine weighs about as much as a toothpick. How does it work without a tether sending power to it? A laser beam. The minuscule circuit attached to its body converts energy from a laser beam into the electricity it needs to power itself. To give it an extra boost, a specially designed circuit and photovoltaic cell provide up to 240 volts to power its wings. But its energy source isn't the only thing that makes this insect superior to Robo-Bee. Unlike Robo-Bee, which also relied on its tether to be controlled by humans, RoboFly has been provided a brain. This specialized brain mimics the brain of a real fly and tells its wing muscles when to flap. A more sophisticated successor to RoboBee, RoboFly is the future of micro-robots. In the near future, RoboFly will be given superior brains.
Number 4. Nadine, the social robot. Continuing the theme of robotic professors, meet Nadine. Modeled on Professor Nadia Magnanat-Thalmann, Nadine isn't merely a mechanical machine. She's a socially intelligent robot, capable of greeting you, enjoying a conversation, and remembering it going forwards. So, she'll be able to pick up your conversation where you left off. She can answer questions in several languages and simulate a certain amount of emotion. Even more impressive, Nadine interacted with more than 100,000 visitors at the Art Science Museum in Singapore. The exhibition, titled Human Plus, The Future of Our Species, was only the beginning. Since, Nadine has met with leading people, from Deutsche Bank to the Prime Minister of India, His Excellency Narendra Modi. Today, she's working 9 to 5 as a customer service agent at AIA Singapore. Ask her any question you'd typically ask a customer service agent, and she'll handle it, regardless of whether you're speaking English, German, Hindi, or Japanese. The secret to Nadine's success is her programmed personality. It's odd to talk of a robot with a personality. After all, isn't it all gears and circuitry? Yet, Nadine's demeanor changes based on the conversation and utilizing a total of 27 degrees of freedom in facial and upper body movements. With such social flexibility, Nadine is paving the way for social robots to assist in helping people with special needs navigate the world. Indeed, Thalmann predicts robots will one day be companions for people living with dementia. As countries worldwide face challenges of an
While the flow of electrons from the metal oxides on the surface of the droplet to the graphite substrate cause vortices and pressure gradients on the inside of the droplet. The variations of the surface tension create a channel that guides the turbulence in the liquid metal on the inside of the droplet.
Now, you might be asking, what exactly is a living robot? And that would be a perfectly reasonable question, especially given the fact that it's being deemed a brand new life form that has never existed before. But before we can actually understand what it does and what that might mean for the future, we have to understand what it actually is. Researchers essentially wanted to figure out if they could take real live cells and make them behave in a way that the researchers wanted them to, much like a robot made of other materials would do. So they took 2 different types of frog cells, both skin and heart cells. Heart cells naturally contract while skin cells don't. So the idea was, if we can put skin cells and heart cells together in a specific way, maybe we can come out with a functional structure that can move. And that's exactly what the researchers tried to do. If you take a look at this video of one of their successful creations, you can see that the blue cells are non-contracting skin cells, while the green and red ones are contracting heart cells. So this particular combination of cells will give you the motion you're seeing in both the animation and the actual result below. But it would have taken a long time to get here. So using computer scientists and evolutionary algorithms, a supercomputer would have made millions of iterations of these combinations of skin and muscle cells to figure out which combinations make the best movements. And evolutionary algorithms would have worked much like natural selection to improve upon existing models to figure out what works better, ultimately ending in what would be deemed the most fit versions.